Hey guys, welcome to this new story. Today, we turn our attention to the moon, the bright world that has followed Earth through the sky for as long as humans have looked up. It may seem familiar, hanging there night after night, but the moon still hides many questions that science has not fully answered. Across its pale surface lie enormous craters, strange glowing flashes, moving shadows, and places that sunlight has never reached. Some regions show signs of deep cracks and long scars, while others hold patterns that appear almost too perfect to be natural. For decades, then telescopes, orbiters, and astronauts have studied this nearby world, yet many of its secrets remain open. Why do some parts of the moon look so different from others? What causes the sudden bursts of light that observers sometimes see on its surface? Why does one side face Earth forever while the other stayed hidden for so long? And what lies deep inside this silent world beneath layers of ancient rock and dust? The moon is the closest world to Earth. It moves around the planet at an average distance of about 384,000 kilometers. From the ground, it appears familiar, a pale circle that changes shape during the month as sunlight reaches different parts of its surface. For thousands of years, people have watched it rise and set, marking time by its slow cycle of phases. Even today, after spacecraft, orbiters, and landers have studied it in detail, one basic question remains partly unanswered. How did the moon form? Modern science has developed several ideas over the past century, but none explain every detail. The most widely accepted explanation is called the giant impact hypothesis. According to this idea, the moon formed more than 4 billion years ago during the early period of the solar system, when planets were still growing through frequent collisions. At that time, the young Earth was still forming. Its surface was much hotter than it is today. Large bodies of rock and metal moved through nearby space, and many of them struck the early planets. Evidence from ancient rocks and computer models suggests that one of these bodies may have been about the size of Mars. This object is often called Theia in scientific discussions. It was not a small asteroid. It was a large planet like body with its own gravity and internal heat. Its path around the Sun slowly changed until one day it crossed Earth's orbit. The collision that followed was not a simple crash. It happened at extremely high speed. Both bodies were pulled together by gravity, and when they met, the impact released an enormous amount of energy. Much of the outer layers of both worlds melted or turned into vapor. Instead of shattering Earth completely, the impact appears to have thrown a large amount of hot rock into space around the planet. This material did not travel far. Earth's gravity kept most of it nearby, forming a wide ring of debris that circled the planet. Within this ring, countless fragments of rock slowly collided with each other. Over time, these pieces joined together through gravity. The larger the growing body became, the more material it attracted. After many thousands of years, the debris formed a single large object. That object became the moon. Computer models show that this process could create a body similar in size to the moon we see today. The theory also explains why the moon orbits in the same direction as Earth's rotation. It even helps explain why the moon formed relatively close to Earth rather than far away in space. However, the story is not completely solved. One of the biggest questions involves the chemical makeup of lunar rocks. When astronauts from the Apollo missions returned samples to Earth, scientists studied them carefully. The results showed something unexpected. The rocks from the moon have nearly the same chemical and isotopic composition as rocks from Earth's outer layers. Isotopes are forms of elements that contain slightly different numbers of particles inside their atoms. These small differences act like chemical fingerprints. Each planet tends to have its own pattern. If the moon formed mostly from the material of another body like Theia, scientists expected the moon to show a different isotopic pattern. Instead, the patterns are almost identical to Earth. This result created a problem. If the moon formed mostly from Earth's own material, the impact must have mixed the two worlds far more completely than early models predicted. Some newer models suggest the collision may have been more violent than first imagined, with both bodies turning into a cloud of hot rock vapor before slowly cooling. In such a case, material from Earth and the impact body would mix together before the moon formed. This mixing could explain why the chemical fingerprints are so similar. Even with these updated models, certain questions remain open, as some elements appear slightly more common in lunar rocks than in Earth's surface. Others are less common. These differences suggest that the moon did not form from exactly the same mixture of material. Another puzzle involves the amount of metal inside the moon. Earth has a large iron core that creates a strong magnetic field. The moon, however, has a much smaller core. If both bodies mixed evenly during the impact, scientists might expect more metal inside the moon. Instead, most of the heavy metal appears to have remained inside Earth. Researchers continue to test different versions of the impact model to explain this difference. Some simulations show that metal from the impact body may have quickly sunk into Earth's deep interior before the moon fully formed. Other models suggest that the moon grew mainly from the lighter outer layers of the debris cloud. The timing of the event is another area of active study. Radioactive dating of lunar samples suggests the moon formed about 4.5 billion years ago. This was very early in the history of the solar system. At that time, the inner planets were still forming through constant collisions with large bodies. Evidence from crater records on the moon also supports the idea that the early solar system was far more violent than it is today. The surface still carries scars from ancient impacts that happened long after the moon formed. Some scientists have proposed other ideas for the moon's origin. One older theory suggested that the moon formed elsewhere in the solar system and was later captured by Earth's gravity. However, this idea struggles to explain the similar chemical makeup of Earth and the moon. Another theory suggested that the moon formed at the same time as Earth from the same disk of material around the young sun. In this case, both bodies would grow side by side. While this idea explains the similar chemistry, it does not easily explain the moon's relatively small iron core or its current orbit. A third proposal once suggested that the moon separated directly from Earth itself. In this model, the young planet spun so fast that a piece of its outer layer broke away and became the moon. Early scientists even suggested that the Pacific Ocean basin might mark the location where the material separated. Modern measurements show that this idea cannot work. The Pacific Ocean formed much later, and Earth's rotation has never been fast enough to throw off a body as large as the moon. Because of these limits, the giant impact idea remains the strongest explanation. Yet the exact details of the event are still under study. Scientists continue to use improved computer models, laboratory experiments, and new measurements of lunar rocks to test how the collision might have unfolded. Recent work has explored an extreme version of the impact. In this scenario, the collision was so powerful that both Earth and the impact body briefly formed a spinning mass of hot rock vapor shaped somewhat like a thick disk. This structure is sometimes called a synestia. Inside this rotating cloud, material could mix very evenly before cooling and forming solid bodies again. The moon might then form from the outer part of this structure, while Earth gathered most of the remaining mass. This model helps explain the shared chemical fingerprints between the two worlds. However, direct evidence is still limited, and scientists continue to compare predictions from different models. New missions to the moon may provide further clues. Future samples collected from regions never visited before could reveal subtle chemical differences across the lunar surface. These differences may record how material settled during the moon's early formation. High precision measurements of the moon's gravity and internal structure also help scientists estimate how the moon cooled and changed after it formed. These data can reveal whether its early interior was completely molten or only partly melted. Each new piece of information helps refine the story, but the full sequence of events remains incomplete. The moon formed from one of the most dramatic events in the history of the Earth Moon system. The collision reshaped the young planet, created a new world in orbit, and set the stage for the stable system that exists today. Even after decades of research, scientists still study the evidence carefully. The rocks returned from the lunar surface hold chemical records of conditions that existed more than 4 billion years ago. Computer models continue to test new versions of the impact. Space missions provide improved maps of the moon's interior and surface. Together, these lines of evidence slowly bring the picture into sharper focus. Yet the exact details of the moon's birth remain one of the largest open questions in planetary science. The event happened long before any direct record could exist. Only scattered clues remain, preserved in rock, motion, and structure. The search to explain those clues continues. The moon keeps one face turned toward Earth. This steady position is not a coincidence. Over long spans of time, gravity between Earth and the moon slowly changed the moon's rotation. The process is called tidal locking. As a result, the same half of the moon always faces the planet below. For many centuries, the other half of the moon remained unknown. Telescopes from Earth could never see it. No matter how powerful the lens became, the far side stayed hidden beyond the curve of the moon. The first clear images arrived in 1959. A spacecraft from the Soviet Union called Luna 3 passed around the moon and sent back grainy photographs of the hidden hemisphere. The pictures were not sharp, but they revealed something surprising. The far side did not look like the side seen from Earth. The difference was striking. The near side contains wide, dark plains. These plains are called maria, a Latin word that means seas. Early observers believed these dark areas were filled with water. Later measurements showed they are not seas at all. They are vast fields of hardened volcanic rock. These maria are easy to see with the naked eye. They form the dark shapes that people often imagine as patterns or figures on the moon's surface. Each maria basin covers thousands of square kilometers. The far side is very different. Instead of wide volcanic plains, the far side is covered mainly with bright highlands. These highlands are older than the maria. They contain countless craters, large and small, spread across nearly every region. Many of the craters overlap each other, showing that the surface has endured repeated impacts over billions of years. The contrast between the two hemispheres is one of the moon's most unusual features. Yet, scientists describe this difference as the lunar dichotomy. One side shows broad lava plains that filled ancient impact basins. The other side remains dominated by rough terrain that has changed little since the early period of the solar system. The question is simple to ask, but difficult to answer. Also, why did volcanic flooding happen mostly on the near side? To understand the puzzle, it helps to look closely at how maria formed in the first place. The dark plains were not created by small eruptions. Instead, they formed when large impacts struck the moon billions of years ago. When a massive asteroid hit the surface, the energy of the impact carved a deep basin. Some of these basins were hundreds of kilometers wide. The force fractured the crust and then allowed molten rock from deep below to rise toward the surface. This molten rock spread across the basin floors. Over time, it cooled and hardened into dark basalt rock. These flows sometimes reach thicknesses of more than a kilometer. The near side contains several large basins that were filled in this way. The Sea of Tranquility, the Sea of Serenity, and the Ocean of Storms are among the best known examples. On the far side, large impact basins also exist, yet most of them were not filled with lava to the same extent. Instead, their floors remained rough and heavily cratered. The difference suggests that something about the moon's internal structure varied between the two sides. Measurements from orbiting spacecraft have provided important clues. Instruments that map gravity and surface elevation show that the crust on the far side is thicker than the crust on the near side. In some places, the difference may reach several tens of kilometers. A thicker crust makes it harder for molten rock to break through to the surface. If lava cannot reach the open basin floor, it cannot spread across the region to form wide plains. This idea helps explain why Maria appear mostly on the near side. The crust there is thinner, allowing molten rock from the mantle to rise more easily after major impacts. But the next question follows quickly. Why is the crust thinner on the near side in the first place? Several possible explanations exist, and scientists continue to test them. One idea involves the early heat of the moon. After the moon formed, much of its interior remained extremely hot. In fact, many models suggest that a large part of the young moon was covered by a global ocean of molten rock. This molten layer is called a magma ocean. As the moon cooled, minerals began to solidify and sink or float depending on their density. Lighter minerals rose toward the top, forming the first crust. Heavier minerals sank deeper into the mantle. If the cooling process happened unevenly, the crust might have formed with different thickness in different areas. Another possibility involves Earth itself. During the moon's early history, the young Earth was still extremely hot. Its surface may have glowed with molten rock after the giant impact that created the moon. Because the moon already faced Earth with one side more often, that side received more heat from the glowing planet. This extra heat may have slowed the cooling process on the near side. If the crust there formed more slowly, it might have ended up thinner than the crust on the far side. This difference could later allow more volcanic activity when large impacts broke through the surface. Computer models have explored this idea in detail. Some results suggest that heat from the young Earth may indeed have influenced the early temperature pattern across the moon's surface. However, the effect may not be strong enough on its own to create the large difference seen today. Another line of research looks at the distribution of radioactive elements inside the moon. Certain elements, such as uranium, thorium, and potassium, release heat as they slowly decay. Measurements from orbit show that these heat-producing elements are more common on the near side of the moon. This region is sometimes called the Procellarum Kuiper terrain. The unusual name comes from the combination of potassium, rare earth elements, and phosphorus found in the area. Because these elements release heat over long periods, regions that contain them can stay warmer inside. Warmer rock is more likely to melt and produce magma. If the near side contained more of these elements early in lunar history, it could explain why volcanic flows happen there more often. The far side, with fewer heat-producing elements, may have cooled faster and remained more rigid. Yet another factor involves the enormous impacts that created the large basins. Some of the biggest basins on the near side formed during a period known as the Late Heavy Bombardment. During this time, large asteroids struck the moon and other inner planets frequently. These impacts may have fractured the crust deeply enough to allow magma to reach the surface in great volumes. Even so, similar impacts also occurred on the far side. The South Pole Aitken Basin, for example, is one of the largest known impact basins in the entire solar system. It stretches roughly 2,500 kilometers across the lunar far side. Despite its enormous size, much of its floor was not covered by the same wide basalt plains seen on the near side. This basin remains an important area of study because it exposes rock from deep inside the moon. Some scientists believe samples from this region could reveal information about the moon's mantle. Spacecraft have already mapped the basin in detail, but future missions may collect rock samples directly from its surface. These samples could help determine why lava flooded some basins, but not others. The contrast between the two hemispheres also affects the moon's appearance when viewed from Earth. The near side shows large, dark shapes because the basalt plains reflect less sunlight than the bright highlands. The far side, lacking these plains, appears brighter overall in photographs taken from orbit. Over time, spacecraft from several nations have mapped both hemispheres with high precision. Modern lunar maps show elevation, mineral content, gravity patterns, and crust thickness across the entire surface. Despite these advances, the full reason for the near far side difference is still debated. Many scientists now believe that several factors worked together: the thickness of the crust, the presence of heat producing elements, the timing of large impacts, and the cooling history of the moon may all have played roles. Instead of one simple cause, the lunar dichotomy may be the result of several processes that acted during the moon's early history. The evidence continues to grow as new missions gather more detailed measurements. Orbiters equipped with spectrometers can identify minerals across wide regions. Gravity mapping reveals how mass is distributed beneath the surface. Laser altimeters measure the height of mountains and basin floors with great precision. Each of these tools adds new information about how the moon formed and evolved. Yet even with these data, the contrast between the two hemispheres remains one of the moon's most striking mysteries. One side displays smooth, volcanic plains formed by ancient flows of molten rock. The other side preserves a record of impacts that stretch back nearly to the beginning of the solar system. Together, they form a natural record of processes that shaped the moon long ago. Understanding why these two halves developed so differently continues to guide lunar research today. The surface of the moon shows only the outer skin of a much deeper world. Mountains, craters, and plains reveal part of its long history, yet they tell little about what lies far below the crust. To understand the moon fully, scientists must study its interior. The structure beneath the surface holds clues about how the moon formed, how it cooled, and how its activity changed over billions of years. Learning about the inside of the moon is difficult. No drilling machine has ever reached more than a few meters into the lunar ground, the deepest direct. Samples came from small core tubes pushed into the soil by astronauts during the Apollo missions. The samples revealed the loose dust and broken rock that cover much of the surface, but they did not reach the solid layers far below. Because direct access is limited, researchers rely on indirect methods. One of the most important tools is the study of moonquakes. These small vibrations travel through the moon in much the same way that earthquakes travel through Earth. By measuring how these waves move, scientists can estimate the structure of the material they pass through. During several Apollo missions in the late 1960s and early 1970s, astronauts placed seismometers on the lunar surface. These instruments were designed to detect ground motion and send data back to Earth. 4 stations remained active for several years. They recorded thousands of signals from different sources. Some of these signals came from impacts. Small meteoroids strike the moon often because the surface lacks a thick atmosphere. When a rock from space hits the ground, it produces vibrations that travel through the lunar interior. These waves carry information about the material they move through. Other signals that came from natural activity inside the moon. Scientists identified several types of moonquakes. Some occurred deep within the interior, possibly caused by tidal forces from Earth pulling slightly on the moon's structure. Others were shallow events that happened closer to the surface. The data from these instruments allowed scientists to build the first basic model of the moon's interior. According to this model, the moon has several main layers. At the top lies the crust. This is the rigid outer shell made mostly of solid rock. The thickness of this layer varies across the surface, but on average, it may be around 50 kilometers thick. Below the crust lies the mantle. This layer makes up most of the moon's volume. The mantle consists of dense rock that was once partly molten during the moon's early history. Over time, it cooled and solidified, but traces of past melting remain in the form of volcanic rock that reached the surface long ago. The deepest layer may be a small metallic core. This core is believed to contain iron mixed with small amounts of other elements, such as sulfur or nickel. Compared with Earth's core, the lunar core is very small. Estimates suggest that the core may measure only a few hundred kilometers in radius. For comparison, Earth's core extends thousands of kilometers from its center. Detecting the presence of this core has been challenging. Seismic waves provide some clues, but the signals are not always clear. The moon's dry, rigid rock causes vibrations to behave differently than they do on Earth. Instead of fading quickly, moonquake waves can echo through the interior for long periods. Some recorded vibrations lasted more than an hour before fading away. This long ringing effect makes it harder to determine exactly where the waves traveled and which layers they crossed. Even with these limits, scientists have identified patterns that suggest the presence of several internal zones. Some studies indicate that the moon may contain a solid inner core surrounded by a liquid outer layer. If this is correct, the liquid portion may consist of molten metal. Evidence for a liquid layer comes partly from the way seismic waves slow down when they pass through certain regions. Liquids transmit some types of waves differently than solid rock. Another line of evidence comes from studies of the moon's rotation. Careful measurements show that the moon wobbles slightly as it moves around Earth. This motion, known as libration, can reveal how mass is distributed inside the body. If the core contains liquid metal, the outer solid layers may shift slightly over it. This movement affects the pattern of the wobble and can be detected through precise tracking of the moon's motion. Laser ranging experiments have helped measure this motion. During the Apollo missions, astronauts placed special reflectors on the surface. These reflectors bounce laser beams sent from observatories on Earth. By timing how long it takes for the laser light to travel to the moon and back, scientists can measure the distance with extremely high accuracy. Repeated measurements over many years reveal tiny changes in the moon's orientation and rotation. These data support the idea that at least part of the lunar core may still be molten. However, the exact size and composition remain uncertain. Some models estimate a liquid outer core with a radius of about 300 kilometers. Others suggest slightly different values depending on how the seismic data are interpreted. Temperature inside the moon is also difficult to measure directly. Heat flow experiments carried out during the Apollo missions provided some information. Instruments were placed in shallow holes to measure the small amount of heat escaping from the interior. The results showed that the moon releases far less heat than Earth. This finding fits with the idea that the moon cooled quickly because of its smaller size. A small body loses heat faster than a large one. Over billions of years, the moon's interior temperature dropped steadily. Much of the early molten rock solidified long ago. Even so, traces of internal heat remain. Some regions of the mantle may still be warmer than others. Radioactive elements within the rock continue to release small amounts of heat as they decay. Understanding the temperature structure is important because it helps explain past volcanic activity. If parts of the mantle remained hot for long periods, they could have produced the lava flows that filled the nearside basins. Gravity mapping from orbiting spacecraft has also provided clues about the moon's interior. These measurements track how a spacecraft's path changes slightly when it passes over areas with different mass beneath the surface. By studying these changes, scientists can estimate how dense the material is at various depths. The results help refine models of the mantle and core. Data from missions such as the Lunar Reconnaissance Orbiter and the Chang'e spacecraft have improved this understanding. The Grail mission, in particular, mapped the moon's gravity field with very high precision. Two small spacecraft flew around the moon while measuring the distance between them using radio signals. Tiny variations in the gravitational pull beneath the surface cause slight changes in this distance. By analyzing these variations, scientists produced a detailed map of mass distribution within the moon. The results showed that the crust is more fractured than once believed, and that many large impact basins changed the internal structure. These impacts may have altered the thickness of the crust and affected how heat moved through the interior. Even with these new measurements, several questions remain open. One question concerns how the core formed in the first place. During the early molten stage of the moon, heavy metal should have sunk toward the center, while lighter rock rose toward the surface. This process, called differentiation, created the layered structure seen today. Yet the moon contains far less metal than Earth. The exact amount that reached the core may depend on how materials separated during the early magma ocean stage. Another question involves the present state of the core. If part of it remains liquid, scientists want to know how much heat is still present and whether slow movement continues within the metal. This movement might once have generated a magnetic field, similar to the field produced by Earth's core today. Evidence from lunar rocks suggests that such a field existed long ago. Understanding the interior layers will also help explain how the moon changed through time. The cooling rate, the thickness of the crust, and the structure of the mantle all influence volcanic activity and tectonic events. Future missions may place new seismometers on the lunar surface to gather more detailed data. A larger network of instruments could detect moonquakes from many directions, allowing scientists to map the interior more precisely. Such measurements could confirm the size of the core, the thickness of each layer, and the temperature pattern deep below the surface. Until that network exists, the interior of the moon remains partly hidden. The ground beneath the craters and plains carries signals that reveal fragments of the story. Each moonquake, each change in gravity, and each rock sample adds another piece of information. Together they suggest a layered world with a small metallic center surrounded by thick rock that has slowly cooled for billions of years. Yet the full structure is still being studied, and many details remain uncertain. The surface of the moon sometimes changes in ways that are difficult to explain. Observers have recorded sudden flashes, both brief glows, and patches of light that appear and disappear quickly. These events, collectively called lunar transient phenomena, or LTPs, have been reported for centuries. Early astronomers, using small telescopes, occasionally saw bright spots that were not present in earlier observations. Some spots lasted only a few seconds, while others persisted for several minutes. Documentation of these events increased as telescopes improved. Astronomers carefully noted the time, location, size, and brightness of each observed phenomenon. Despite careful records, the causes of these flashes remain uncertain. Observers sometimes saw reddish or bluish glows, color shifts, or sudden bright areas. The unpredictable nature of these events makes them difficult to study systematically. Some LTPs have been linked to sunlight reflecting off the edges of deep craters. In certain cases, low sunlight angles can create bright spots along crater rims or mountain edges. However, many events do not correspond with simple reflection. In these cases, the brightness appears in the middle of flat plains or in locations without sharp terrain features. Another possible explanation involves small impacts. The moon is constantly struck by tiny meteoroids. These impacts can release bursts of light as the kinetic energy of the object is converted into heat and light on impact. Observers have reported flashes that match the expected brightness of meteoroid impacts. Some LTPs have been confirmed by modern cameras placed in lunar orbit, which recorded meteoroid impacts in real time. Gas release from the lunar interior may also play a role. Even though the moon is largely inactive today, there are areas where trapped gases may accumulate beneath the surface. Small eruptions or seepage of these gases through cracks in the crust could create temporary brightening or color changes. Lunar samples indicate that gases such as argon and radon exist in small amounts within the regolith. Instruments placed on the surface during the Apollo missions detected sporadic increases in gas concentrations, suggesting slow leaks or bursts. The interaction of solar radiation with the surface may also contribute to some LTPs. Solar wind particles strike the moon continuously, and charged particles can excite minerals at the surface. In certain conditions, this process could produce faint glows or color changes visible from Earth or orbit. While this mechanism is weaker than impact flashes, it may explain some of the more subtle phenomena. Volcanic activity is unlikely to be the main source of modern LTPs, but evidence from lunar history shows that molten rock once reached the surface. The moon experienced widespread volcanic flows billions of years ago. Some scientists have speculated that residual heat or isolated pockets of molten material could occasionally rise to the surface, producing localized brightening. No direct evidence of this has been observed in the past decades, but the idea is considered in models of possible internal activity. The locations of reported LTPs are not random. Certain regions, such as the edges of large basins or deep crater floors, appear more frequently in the records. For example, the Aristarchus Plateau has been a site of repeated observations. Its high albedo and prominent topography make it more noticeable, but repeated events suggest additional factors are involved. Observers have reported hundreds of transient events in this region over the past century. Brightness changes are measured in several ways. Some reports describe increases in light intensity relative to surrounding terrain. Others note that the phenomenon appears as a color shift, often reddish, bluish, or yellowish. Duration varies from seconds to several hours, though the longest lasting events are rare. Short events are difficult to confirm because multiple observers rarely view the same region simultaneously. Longer events provide more opportunities for verification. Modern telescopes and spacecraft continue to monitor these phenomena. Orbital cameras can detect small impacts and measure variations in reflected light. Some instruments who use ultraviolet or infrared wavelengths to capture changes not visible to the human eye. These observations help separate real physical events from optical illusions caused by the Earth's atmosphere, telescope optics, or observing conditions. Despite improved monitoring, the unpredictable nature of LTPs makes them difficult to study statistically. Some astronomers believe that many reports from historical records may include observational errors or transient atmospheric effects. Others argue that a significant number of events are real physical changes on the moon's surface. The balance between these possibilities is still a matter of scientific debate. Reports of LTPs sometimes coincide with meteor showers. During periods of increased meteoroid flux, more impact flashes are expected. These flashes match the location and duration of some historical observations. However, many LTPs occur at times when meteor activity is low. This discrepancy suggests that not all transient phenomena are caused by impacts. Seismic studies offer another approach to understanding LTPs. Moonquakes can produce small surface movements that may slightly shift dust or rocks. Such shifts could temporarily change the way sunlight reflects from a region, creating the appearance of a brightening. Analysis of seismometer data from the Apollo missions shows that some shallow moonquakes occur in areas where LTPs have been reported, though the correlation is not perfect. The moon's surface contains fine regolith, composed of broken rock and dust. This layer can shift due to impacts, thermal expansion, or vibration from quakes. When layers move, they can alter the local reflectivity and produce brief, bright, or dark spots. This process is subtle, but may explain certain types of LTPs, particularly those lasting only a few seconds. Electrostatic effects have been proposed as another factor. The lunar surface accumulates electric charge due to the constant bombardment of solar wind particles. Under specific conditions, charged dust particles could levitate or move across the surface. Such movement may reflect sunlight in unusual ways, creating transient bright patches. Experiments and models suggest that electrostatic levitation is possible, especially near the terminator, where sunlight meets shadow. Color shifts reported in LTPs remain particularly challenging to explain. Mineral composition alone does not change quickly. Therefore, temporary color changes likely involve light scattering, thin dust layers, or transient gas emission. Ultraviolet and infrared observations can sometimes detect small emissions of energy in addition to visible light, hinting at processes below the surface. A combination of factors may be responsible for many LTPs. Impacts, gas release, seismic shifts, and electrostatic effects could all act together. The observed brightness, color, and duration of each event may result from several mechanisms occurring simultaneously. This complexity is why no single explanation covers all observations. The Lunar Reconnaissance Orbiter and other spacecraft continue to monitor the Moon for new events. High-resolution imaging and laser altimetry allow scientists to measure any changes in topography that might accompany flashes or glows. Instruments designed to detect gas release provide additional data about ongoing activity beneath the surface. Researchers also maintain historical catalogs. They compare old reports with modern observations to identify recurring locations or patterns. Sites with repeated LTPs can be prioritized for further study, including potential lander missions designed to record events on the surface with high-speed cameras and sensors. One challenge is differentiating real phenomena from observational errors. Atmospheric turbulence on Earth can distort images, causing apparent brightening or color change. Even minor clouds or haze can create effects that resemble a flash on the Moon. High-resolution orbiting cameras help verify events by removing Earth-based interference. Another challenge is predicting when LTPs will occur. Because they are sporadic and brief, setting up instruments to observe the exact location at the right time is difficult. Long-term monitoring, often with multiple instruments and sites, is necessary to capture reliable data. In summary, lunar transient phenomena remain a partially explained aspect of the Moon's behavior. Observers have recorded flashes, glows, and color changes for centuries. Some events can be linked to impacts, sunlight reflections, or gas release. Others may involve seismic movement, electrostatic effects, or combinations of these processes. Modern instruments continue to study the phenomena, though unpredictability and variability make definitive answers elusive. LTPs represent a subtle, ongoing interaction between the Moon's surface, its shallow interior, and the environment of space that surrounds it. Near the poles of the Moon, some craters never receive sunlight. The Moon's axis is tilted only slightly, about 1.5 degrees, so sunlight reaches the floor of these craters only at very shallow angles, if at all. As a result, some depressions are in permanent shadow. These areas are called permanently shadowed regions, or PSRs. Inside these craters, temperatures remain extremely low, often below -240 degrees Celsius. Such cold conditions allow materials that would normally evaporate on the Moon's surface to remain solid for long periods. The discovery of these shadowed regions came from spacecraft observing the lunar poles. Early maps showed deep craters and uneven terrain at the north and south poles. Subsequent measurements revealed that some of these craters never received direct sunlight. Radar instruments and infrared sensors later confirmed the extreme cold in these regions. PSRs are scientifically important because they may contain water ice. Water ice does not survive on most of the Moon's surface due to sunlight, which causes it to sublimate. In permanently shadowed regions, the extreme cold traps water and other volatile materials. This makes these craters potential reservoirs of frozen water, preserved for millions or even billions of years. Evidence for ice comes from multiple sources. Radar instruments on orbiters detect highly reflective surfaces consistent with water ice. Neutron detectors measure hydrogen, which may indicate the presence of water. Infrared measurements provide further support by revealing low temperatures and possible ice deposits. These combined observations suggest that the poles contain significant quantities of frozen water in some locations. The distribution of ice within PSRs is not uniform. Some craters appear to contain dense concentrations near their floors, while others have only sparse or patchy deposits. Small scale topography, depth, and surface roughness all affect how ice accumulates and persists. Some regions may have shadows that are not complete, allowing sunlight to reach certain slopes, which limits the stability of ice there. The origin of the ice is also under investigation. One source is believed to be cometary impacts. Comets contain water, and when they collide with the moon, part of this water may remain trapped in cold regions. Another source is the solar wind. Hydrogen ions from the sun may interact with oxygen in the lunar soil to form small amounts of water, which can migrate to shadowed craters. Once water reaches a PSR, it can remain for extremely long periods. The low temperatures prevent sublimation, and the absence of atmosphere reduces the loss of material to space. Over time, small inputs of water from impacts or solar wind accumulate, forming layered deposits. Some models suggest ice could be mixed with lunar soil, forming a combination called regolith ice. The depth of ice deposits is difficult to measure. Radar and neutron measurements provide clues about surface and near surface concentrations, but they cannot reveal layers buried deep below. Some ice may exist only a few centimeters below the surface, while other areas could have deposits several meters thick. Determining the total volume remains a central goal of lunar science. Temperature variation within PSRs is small but important. Some areas may reach minus 220 degrees Celsius during rare moments of partial sunlight or scattered illumination. Even small temperature changes affect the stability of ice. Shadowed crater floors are uneven, and slopes facing tiny light sources may experience localized warming. The material covering ice deposits also influences their preservation. Regolith, the layer of dust and broken rock covering the moon, can act as an insulating blanket. A thin layer of dust protects ice from small micrometeorite impacts and from minor heat input. Over long periods, this process helps maintain stability. Permanently shadowed craters are not only cold traps, they also capture other volatiles, such as carbon dioxide, ammonia, and methane. These compounds are even more fragile than water ice, and their presence provides additional information about how material migrates on the moon and accumulates in cold traps. Detailed mapping of PSRs comes from instruments such as the Lunar Reconnaissance Orbiter's LEND and LOLA sensors. LEND detects neutrons released by cosmic rays interacting with hydrogen-rich material, revealing concentrations that may indicate water. LOLA measures the exact shape of the terrain and the depth of shadows. Combining these data allows scientists to estimate the size and location of ice-rich regions with high precision. The study of PSRs also provides insight into the thermal history of the moon. By measuring how cold these regions remain, scientists can infer how well heat moves through the lunar crust. Observations show that the interiors of deep craters are insulated effectively, with little warming over time. This suggests the moon's surface and shallow crust are very poor conductors of heat. Understanding these regions is critical for planning future exploration. Water is essential for life support and can be converted into fuel for spacecraft. If large deposits exist in PSRs, future missions could potentially access these resources. However, landing and operating in these craters is challenging due to their darkness, steep slopes, and extreme cold. Remote sensing continues to improve knowledge about PSRs. Higher resolution radar and spectrometer measurements help identify small patches of ice and their purity. Some studies suggest that ice may be mixed with lunar soil at a ratio that varies depending on location. In certain areas, pure ice may exist near the surface, while in others, it may be deeply buried or distributed in small grains. The lunar poles themselves are surrounded by rugged terrain. Mountains, ridges, and crater rims create complex patterns of illumination and shadow. Even small changes in slope can determine whether a location receives occasional sunlight or remains in permanent shadow. Understanding this microtopography is essential to predict where ice is most stable. Interactions with micrometeorites can alter the surface of PSRs over time. Tiny particles constantly strike the lunar surface, churning the regolith and exposing or burying ice. These processes are slow but continuous, gradually reshaping the upper layers of permanently shadowed craters. Seasonal changes on the moon are minimal due to its small axial tilt, but the angle of sunlight near the poles still varies slightly over the lunar year. These variations can influence the edges of PSRs, sometimes exposing narrow ridges to brief sunlight while keeping the crater floor in shadow. Such marginal areas are critical for understanding how ice survives over long periods. Studying PSRs also aids in understanding the moon's chemical cycles. Volatile compounds trapped in shadowed regions represent a frozen record of material delivered over billions of years. Cometary impacts, solar wind contributions, and micrometeorite delivery are all recorded in these deposits. Analyzing their composition can reveal details about the history of the inner solar system. Advanced simulations suggest that PSRs may contain small pockets of pure ice alongside layers mixed with regolith. Some ice may have crystallized into stable structures, while other material may remain loosely bound within dust grains. Temperature and impact history influence these arrangements. The distribution of ice in PSRs is highly variable. Some craters have floors covered almost entirely with ice, while others have scattered patches concentrated in corners or depressions. Understanding the spatial pattern is important for both scientific study and potential exploration. In addition to water and volatiles, PSRs preserve evidence of lunar history. Layers of regolith record impacts, micrometeorite activity, and space weathering. Deep shadow prevents sunlight from altering these surfaces, making PSRs natural archives of ancient processes. Continued observation with orbiters, combined with sample return missions, may provide direct confirmation of ice content and depth. Instruments capable of drilling or analyzing subsurface layers will clarify how much water exists, its purity, and its spatial extent. Overall, permanently shadowed craters at the lunar poles represent one of the moon's most unusual environments. They remain extremely cold, contain frozen volatiles, and preserve material for potentially billions of years. Studying them provides insight into the moon's formation, thermal history, delivery of water and other compounds, and opportunities for future exploration. Evidence from lunar rocks shows that the moon once had a magnetic field. These rocks, collected during Apollo missions, contain minerals that align with magnetic fields as they cool. Measurements reveal that some rocks formed billions of years ago preserve a record of magnetization, indicating that a global magnetic field existed at the time of their formation. The presence of a magnetic field suggests that the moon once had an internal dynamo. On Earth, the magnetic field is generated by the movement of molten iron and other metals in the outer core. A similar process may have occurred on the moon when it was young and hotter. The movement of conductive material could have produced electric currents, which in turn generated a magnetic field across the entire body. Magnetic signatures in lunar rocks vary with age. The oldest samples, dating from about 4 billion years ago, indicate a relatively strong magnetic field. These ancient rocks suggest the moon's field may have been comparable in intensity to Earth's field at that time. Later rocks, formed roughly 3 billion years ago, show weaker magnetization. By about 1 billion years ago, new rocks show almost no evidence of a magnetic field. This pattern implies that the moon's magnetic field was strongest during the early period of its history and gradually weakened over time. Understanding the cause of both the early strength and the later decline is a central question in lunar science. One proposed explanation involves the early heat of the moon. When the moon formed, it was hot inside. The core may have contained a mixture of molten iron, sulfur, and other metals. As these materials moved, they could have created the currents necessary for a magnetic dynamo. Over time, the moon cooled, and much of the core solidified. A solid core cannot generate the same electrical currents, leading to the weakening and eventual disappearance of the magnetic field. Another factor may involve the size of the moon's core. Unlike Earth, the moon's core is relatively small. A smaller core contains less molten metal, which may limit the duration and intensity of a dynamo. Combined with rapid cooling due to the moon's small size, the internal dynamo may have stopped operating after only a few 100 million years. Impacts may have influenced the magnetic field as well. Large collisions early in lunar history could have injected energy into the interior, stirring molten metal and temporarily enhancing the dynamo. Some researchers propose that repeated impacts created fluctuations in the field, recorded in rocks of different ages. Analysis of rock magnetization also shows that the field may have reversed direction occasionally. Like Earth's magnetic reversals, the lunar field may have flipped north and south over time. These reversals are recorded in the orientation of minerals within ancient basalt flows. Understanding the timing and frequency of these reversals helps scientists model the behavior of the lunar dynamo. The mechanism for generating the magnetic field may have differed from Earth's. Some studies suggest the early moon could have used a combination of thermal convection and crystallization in the core. As the core cooled, crystallization of iron may have caused movement of the remaining liquid metal, producing magnetic fields. This crystallization-driven dynamo could explain how the field persisted even after the moon's interior began to solidify. Other models consider mechanical forces caused by tidal interaction with Earth. The gravitational pull of Earth creates stress and slight deformation in the moon's interior. During the early history, when the moon was closer to Earth, these tidal forces were stronger. Some researchers propose that these stresses could have helped maintain motion in the liquid core, supporting a dynamo over a limited period. Magnetic fields may also leave evidence in other materials. Tiny metallic grains found in lunar soil can record magnetic information when they cool. Careful laboratory analysis of these grains allows scientists to reconstruct aspects of the ancient field, including direction and intensity. The disappearance of the field has implications for surface conditions. Without a global magnetic field, the moon lost protection against solar wind and cosmic radiation. Over billions of years, the solar wind has implanted particles into the regolith while stripping away any remaining atmosphere. The lack of magnetic shielding has shaped the surface chemistry and exposed materials directly to space weathering. Understanding the ancient lunar field also informs models of planetary evolution. A magnetic field is evidence of internal activity. The moon's early dynamo shows that even small celestial bodies can produce global magnetic effects, but only while heat and motion in the core remain sufficient. Recent missions have sought additional evidence of the past field. Orbiters equipped with magnetometers have measured variations in surface magnetism. Some regions retain remnant magnetization in crustal rock, even though the global field is gone. These magnetic anomalies suggest local concentrations of magnetized rock, perhaps caused by early dynamo activity or impact events. Magnetic studies thus help identify regions with unusual crustal composition. Strong anomalies often correspond to areas with basalt flows or dense rock. Mapping these anomalies contributes to understanding the moon's thermal and volcanic history, linking internal processes with surface geology. Laboratory analysis complements orbital measurements. Scientists examine thin sections of returned rock samples under sensitive magnetometers, carefully isolating the original magnetic signal from any later interference. These studies have shown that magnetization varies with rock type, location, and age. Basalt flows generally show stronger records of ancient fields than in orthosite highlands, reflecting differences in formation processes and temperature histories. Some rocks also indicate that local magnetic fields may have existed even after the global field declined. These local fields could arise from rapid cooling of small pockets of molten rock or magnetization from impact generated shock waves. Such local anomalies provide a more detailed picture of the moon's magnetic evolution over time. Understanding the source and disappearance of the moon's magnetic field remains an active area of research. While many models exist, including thermal convection, crystallization dynamos, and tidal effects, no single explanation is universally accepted. Combining observations from lunar rocks, orbiting instruments, and laboratory experiments continues to refine theories. The intensity of ancient lunar magnetism also varies geographically. Some regions show stronger preserved magnetization than others. This pattern suggests that internal processes were uneven, influenced by the distribution of heat producing elements, mantle dynamics, and crustal thickness. Areas with thinner crust may have transmitted magnetic effects more efficiently to the surface. Finally, studying the moon's magnetic history provides context for other bodies in the solar system. Small planets and moons may experience similar temporary magnetic fields. Comparing lunar data with records from meteorites or Mars helps scientists understand the conditions under which magnetic dynamos can operate and why they eventually cease. The combination of rock magnetization, orbital mapping, and theoretical models forms a picture of a once magnetic moon. Its field was strong in the earliest billion years, likely generated by movement in a molten core. Over time, cooling and solidification caused the field to weaken and disappear. Remnants of this field are preserved in rocks and crustal anomalies, providing a window into the moon's early internal activity and thermal history. Seismometers placed on the moon during the Apollo missions recorded vibrations that were unusual compared with earthquakes on Earth. These moonquakes occur at different depths and intensities, and some last far longer than typical terrestrial quakes. While earthquakes usually fade within seconds to minutes, certain moonquakes can continue for up to an hour, producing a long, ringing vibration through the lunar crust and upper mantle. Scientists have classified moonquakes into several types. Deep moonquakes occur hundreds of kilometers below the surface. These are thought to be triggered by tidal forces as the moon orbits Earth. The gravitational pull of Earth slightly stretches and compresses the moon's interior, producing regular, repeating quakes at predictable times and locations. Shallow moonquakes, on the other hand, occur much closer to the surface. They are less frequent, but can be more energetic, causing local surface displacement and temporary changes in stress. Within the crust, thermal quakes are another type. They occur when sunlight heats the surface at the lunar morning, causing expansion of the upper regolith and shallow crust. The rapid temperature change produces stress that fractures the rock, producing small vibrations detectable by seismometers. Although weaker than deep or shallow quakes, thermal quakes occur daily and contribute to the ongoing modification of the lunar surface. Impact-induced quakes are generated when meteoroids strike the moon. Unlike Earth, the moon has no significant atmosphere to burn up small objects before impact. Even tiny meteoroids can produce vibrations that propagate through the interior. Large impacts create detectable signals across the entire network of Apollo seismometers, providing insight into the energy transferred during collisions and the moon's ability to transmit vibrations. One of the most striking aspects of moonquakes is their duration. The low density and fractured nature of the crust allows seismic waves to propagate with little attenuation. In contrast to Earth, where waves are quickly absorbed by dampening effects in water, soil, and complex layered rock. The moon's dry, rigid interior permits vibrations to continue for extended periods. This long ringing is one reason that moonquakes feel unusual when compared to terrestrial quakes. The structure of the moon influences the behavior of seismic waves. The crust is highly fractured, with countless cracks from ancient impacts. Beneath the crust lies the mantle, composed of dense rock with traces of past molten activity. Seismic waves travel differently through these layers. They may slow, reflect, or refract depending on material density and composition. The variation in wave behavior provides scientists with data about the internal structure, even without direct access. Seismometer data reveal the locations of moonquake epicenters. Deep quakes are typically found in narrow zones, hundreds of kilometers below the surface, consistent with tidal stress models. Shallow quakes tend to cluster in regions with thick or complex crust, suggesting structural weaknesses. These patterns allow researchers to map the interior and understand stress distribution across the moon. Moonquakes also indicate that the moon is not entirely inactive. Even though it lacks active plate tectonics or significant volcanism today, internal forces continue to produce measurable activity. This activity is subtle, but the persistence of quakes demonstrates that the moon's interior retains some flexibility. The slight motion caused by tides, combined with residual heat in the mantle, maintains internal stress and occasional movement. Analyzing moonquake waves provides information about the properties of lunar rock. The speed at which waves travel depends on density and rigidity. By comparing observed wave speeds with models of different rock types, scientists can infer the composition of crust and mantle layers. These analyses show that the upper crust is fractured and porous, while deeper layers are more solid, consistent with early cooling and solidification. Some moonquakes appear to be related to faults. Cracks in the crust may move gradually or suddenly, producing vibrations. The moon's lack of atmosphere and water reduces erosion, allowing faults to persist for long periods. Active faults may respond to tidal stretching, triggering sudden displacement and the associated seismic waves. The timing of moonquakes is often predictable for deep events. These quakes occur roughly every month at intervals corresponding to the lunar orbital cycle. This regularity matches the pattern of tidal stress, as the gravitational pull of Earth reaches maximum effect at certain points in the orbit. Such regularity allows scientists to model the stress environment of the lunar interior with high precision. Seismic data also indicate that some shallow quakes may occur unpredictably. These events can produce moderate shaking at specific sites, causing minor disturbances in the regolith. Because the shallow crust is highly fractured, stress can build in localized areas and release suddenly. These shallow moonquakes provide insight into the mechanical properties of the upper lunar crust. The energy released by moonquakes is smaller than that of major earthquakes, but significant for the moon. Seismometers detected vibrations that would correspond to a magnitude 4 or 5 earthquake on Earth. In the absence of atmosphere and water, these vibrations can affect loose surface material and create minor shifts in the regolith. Over time, this contributes to the slow alteration of crater walls and surface slopes. Moonquake research also has implications for future lunar exploration. Sensitive instruments must be designed to withstand vibrations that last longer than earthquakes. Habitats and equipment placed on the surface could experience prolonged shaking, and understanding the magnitude, frequency, and depth of moonquakes is essential for planning stable operations. In addition to Apollo-era seismometers, orbiting spacecraft have contributed indirect data. Observations of the surface over time, combined with high-resolution imaging, allow scientists to correlate small changes in crater walls or slopes with potential seismic activity. These studies provide an extended record of motion, complementing the direct measurements from surface instruments. Internal heat in the moon plays a role in sustaining seismic activity. Although the interior has cooled considerably since the moon's formation, residual heat in the mantle may create convection currents on a very small scale. These currents could maintain slight motion in localized regions, contributing to stress accumulation in the overlying crust. The magnitude of this heat driven motion is small, but it may explain some of the more subtle, long lasting vibrations. The moon's internal activity is also connected to its orbital history. As the moon gradually recedes from Earth, tidal forces change slowly over millions of years. This slow evolution affects the stress applied to the crust and mantle. Studying current moonquakes helps scientists understand how these forces operate over geological timescales. Comparisons with other celestial bodies provide context. Mercury, for example, experiences seismic activity influenced by tidal forces and thermal contraction. By studying the moon, scientists can learn how small, airless bodies respond to internal and external stresses. These comparisons also assist in planning missions to other moons or asteroids where vibrations may affect surface operations. Moonquakes produce complex waveforms. Primary waves travel fastest, compressing rock along the direction of motion. Secondary waves move more slowly, causing shearing motion. Surface waves travel along the uppermost layers, often producing the longest lasting vibrations detected by seismometers. The combination of wave types contributes to the extended duration of shaking observed on the moon. Some seismic signals remain unexplained. Occasionally, instruments detect vibrations without clear origin, neither linked to tidal stress, thermal expansion, nor impacts. These events suggest that minor internal adjustments, previously unrecognized, may occur. Ongoing analysis seeks to identify their source, providing insight into subtle processes operating deep within the moon. Researchers also study the cumulative effects of repeated moonquakes. Over millions of years, even low intensity vibrations can alter the upper crust, redistributing dust and fine rock. The slow movement of material, combined with micrometeorite impacts, gradually shapes the lunar surface. These processes provide context for understanding regolith layering, crater degradation, and small slope failures. Seismic activity contributes to a broader understanding of lunar geology. Faulting crystal, fractures, and stress accumulation all connect surface features with interior processes. By linking moonquake data with geological mapping, scientists can reconstruct the moon's structural evolution and identify regions where internal stress remains active. Future missions may deploy more sensitive seismometers across a wider range of locations. A denser network would allow scientists to triangulate quakes with greater precision, determine variations in wave speed with depth, and distinguish between different types of seismic sources. Such information will improve understanding of the moon's interior and ongoing activity. Ultimately, moonquakes demonstrate that the moon is not completely inert. Despite lacking plate tectonics, volcanism, or a substantial atmosphere, internal stresses continue to produce measurable motion. These vibrations reflect the interaction between tidal forces, residual heat, crustal structure, and impact history. Monitoring and interpreting moonquakes provide essential knowledge about the moon's interior and its current state of activity. Across the moon's surface, bright, curved markings appear in several locations. These features, called lunar swirls, form distinct patterns that do not match ordinary geological formations. Swirls are typically narrow, sinuous, and sharply defined, creating a contrast against the surrounding terrain. Their bright appearance indicates they are less weathered than neighboring regions, suggesting that the surface material in these areas has experienced different exposure conditions over long periods. Lunar swirls often coincide with localized magnetic anomalies. Orbiting magnetometers have detected small regions where the magnetic field is stronger than in surrounding areas. These anomalies are irregular in shape and vary in intensity. In many cases, the swirl patterns align with these magnetic concentrations, hinting at a connection between surface brightness and local magnetism. The precise formation mechanism of lunar swirls remains uncertain. One explanation involves the deflection of charged particles from the solar wind. On the moon, the solar wind constantly bombards the surface, breaking down minerals and darkening the soil. Magnetic anomalies may locally shield the surface from these particles, preserving the original brightness of the regolith. In this way, the swirls remain bright while nearby regions gradually darken. Swirls are often found on older, heavily cratered terrain. The regolith in these regions has been exposed for billions of years, experiencing continuous weathering from micrometeorite impacts and solar radiation. The brightness of swirls suggests that this weathering process has been interrupted or reduced. Magnetic shielding provides a plausible explanation, though it does not account for all observed patterns. Some swirls appear along crater rims or in the vicinity of small impact sites. These associations suggest that impacts may influence the creation or modification of swirls. One hypothesis proposes that impacts could expose underlying magnetic material or enhance existing localized fields, thereby affecting how solar wind interacts with the regolith. The resulting bright markings could follow curved or spiral paths dictated by magnetic field lines. Swirls vary in scale. Some are only a few tens of meters wide, while others extend for tens of kilometers. Their shapes include loops, elongated curves, and irregular meanders. The pattern complexity indicates that multiple factors, including magnetic field geometry, impact history, and local topography, influence their formation. High-resolution imaging from orbiters has allowed detailed mapping of these patterns, revealing fine-scale structures that were previously invisible. Spectral studies of swirls provide additional insight. Instruments measuring reflected light in different wavelengths show that swirl material is compositionally similar to surrounding soil. The brightness difference arises mainly from variations in maturity, a measure of how long the surface has been exposed to space weathering. Less mature regolith in swirls suggests protection from darkening processes or recent exposure of fresh material. Magnetic measurements support the idea of local protection. Stronger anomalies so correlate with brighter swirls, indicating that localized fields can influence how charged particles interact with the surface. Variations in anomaly strength may account for differences in swirl intensity, width, and shape. However, not all swirls perfectly align with magnetic highs, implying that additional factors may contribute. Some researchers propose that electrical currents generated by meteorite impacts could also create swirl patterns. As an impact strikes, it generates a magnetic pulse and redistributes charged particles across the surface. This interaction may temporarily enhance magnetic protection, contributing to the development of bright swirls. Over time, repeated impacts and particle flux could maintain or modify the pattern. Observations of swirls over multiple decades show little change in brightness or shape, confirming that they are stable features. Unlike transient phenomena, which last only seconds to minutes, swirls persist for millions or billions of years. This longevity supports the idea that they reflect a balance between regolith aging processes and local protective mechanisms. Swirls appear on both the near side and far side of the moon. However, they are more common in certain regions, particularly around large basins, such as Gini and Reiner Gamma. These concentrations may indicate underlying differences in crustal composition, magnetic properties, or the history of impact events in these areas. The relationship between swirl formation and crustal composition remains under investigation. Some regions with swirls have higher concentrations of iron-rich minerals, which could enhance magnetic properties. Others appear in areas with different regolith types, suggesting that the process is not limited to a specific material but interacts with multiple factors, including topography, mineral content, and impact history. The geometry of magnetic anomalies may shape the appearance of swirls. Field lines emerging from magnetic highs may create loops, arcs, or meanders that correspond to the observed brightness patterns. Swirls often extend along curved paths that reflect the direction of these fields. Mapping the alignment of swirls with magnetic vectors helps scientists understand the link between surface features and internal properties. In some cases, swirls appear near small volcanic deposits or ancient lava flows. Although these features are largely inactive today, localized heating or compositional differences may have influenced magnetic characteristics during formation. The presence of swirls on volcanic terrain suggests that multiple formation mechanisms may overlap or interact over time. The scale and complexity of swirls indicate that they are not purely a surface phenomenon. Interaction between the moon's crust, magnetic field, and solar environment likely determines the appearance, brightness, and patterning. The fact that swirls are sharply defined and persistent over billions of years makes them unique markers of surface environment interactions. High resolution imagery shows that swirls often have a distinct boundary between bright and dark material. This boundary is abrupt, suggesting that whatever process protects or exposes the swirl material acts over a short spatial range. Such precision supports the idea of magnetic shielding, as fields decrease sharply away from localized highs, producing well-defined edges. Some models suggest that the combination of small impacts, solar wind deflection, and remnant magnetic fields produces a feedback loop. As particles are deflected from magnetic highs, surface brightness remains high. Subsequent impacts may modify the field locally, reinforcing the pattern. This loop could explain the intricate, curved nature of many swirls and their long-term stability. The study of lunar swirls contributes to understanding space weathering. By comparing the brightness, composition, and magnetic properties of swirls with surrounding terrain, scientists can estimate how quickly regolith darkens under solar wind and micrometeorite bombardment. Swirls serve as natural laboratories for observing the effects of radiation and particle flux over geologic time. Observations in multiple wavelengths, including visible, ultraviolet, and infrared, provide additional information. Ultraviolet and infrared imaging can reveal subtle differences in temperature, mineral content, and surface roughness. These data help clarify why swirls maintain their brightness and how the solar wind interacts with magnetically shielded areas. Swirls also provide insight into the moon's magnetic history. Localized anomalies may be remnants of ancient global fields or produced by concentration of magnetic minerals. Studying swirls and their associated magnetic features can reveal the timing and persistence of magnetic activity, connecting surface observations to internal processes. Finally, lunar swirls illustrate the complexity of interactions between surface, space environment, and internal properties. Their distinct patterns, persistence, and association with magnetic anomalies make them one of the moon's most intriguing surface features. Ongoing mapping, spectral analysis, and magnetic measurements continue to refine understanding of these unusual formations, offering clues about both current and ancient lunar processes. Beneath the surface of the moon, certain regions contain unusually dense concentrations of mass. These areas are often found beneath large impact basins and are known as mascons, short for mass concentrations. Mascons affect the gravitational field locally, creating variations that influence the motion of orbiting spacecraft. When early lunar satellites passed over these regions, their trajectories shifted slightly, revealing the presence of unexpected mass beneath the crust. Mascons are typically associated with large ancient impact basins. The collisions that formed these basins were extremely energetic, excavating vast amounts of rock and creating depressions hundreds of kilometers wide. Over time, the basins were partially filled by volcanic lava flows, which introduced denser material into the crust. The combination of thick basaltic deposits and mantle uplift contributed to the high-density anomalies observed today. The detection of mascons changed early expectations about the moon's internal structure. Before satellite measurements, scientists assumed that the moon had a relatively uniform interior, with density gradually increasing toward the center. The discovery of localized mass concentrations showed that the crust and upper mantle are more heterogeneous than previously thought. These variations provide important clues about the moon's geological and thermal history. Mascons affect spacecraft orbits by creating subtle but measurable deviations from a smooth path. As a satellite passes over a region of higher gravity, it is drawn slightly closer to the surface, increasing speed temporarily. Conversely, leaving the region causes the satellite to slow as it moves into lower gravity. By carefully tracking these orbital changes, scientists can map the location, size, and intensity of mass concentrations with high precision. The gravity anomalies associated with mascons are strongest near the center of large basins, where dense basaltic fill is thickest. Surrounding areas often show smaller deviations, gradually blending into the normal gravitational field. The shape and distribution of these anomalies provide insight into the original impact event, the thickness of subsequent lava flows, and uplift of underlying mantle material. Mascons are not uniformly distributed across the moon. They primarily occur beneath basins on the near side, such as Mare Imbrium, Mare Serenitatis, and Mare Crisium. The far side contains fewer large basins and less dense volcanic fill, resulting in weaker or absent mascon signals. This uneven distribution reflects differences in crustal thickness, volcanic activity, and impact history between the two hemispheres. The formation of mascons involves both mechanical and thermal processes. Large impacts create fractures in the crust and may cause partial uplift of mantle rock. Subsequent volcanic activity fills the basin with dense basalt, which cools and solidifies. Cooling causes contraction, slightly changing the distribution of mass. Together, these processes produce the concentrated anomalies detected today. The study of mascons also provides clues about the moon's interior. The way the crust and mantle respond to large impacts indicates the mechanical properties of these layers. For example, the depth and magnitude of mascon-related gravity peaks help scientists estimate crustal thickness, density of basaltic fill, and the elastic behavior of the mantle. Understanding these properties is essential for modeling lunar formation and evolution. Mascons influence more than just spacecraft motion. The variations in gravity can also affect regolith movement over geological time. In regions with slightly stronger pull, material may migrate downslope or settle differently, contributing to subtle changes in surface topography. While the effect is small, over millions of years, it can alter crater floors and basin interiors. The relationship between mascons and volcanic activity is significant. Most large basins with mascons are filled with basalt, which is denser than the surrounding highland rock. This fill contributes to the gravitational anomaly. The timing of lava emplacement relative to the impact event affects the structure of the mascon. Early flows may produce different patterns than later ones, leaving a record of volcanic history within the gravitational field. Some mascons exhibit complex internal structures. Detailed gravity mapping shows that the center of the anomaly may not coincide exactly with the geometric center of the basin. Variations in basalt thickness, uneven uplift, and secondary impacts all influence the exact distribution of mass. These complexities challenge simple models and suggest that each mascon has a unique formation history. Mascons also interact with the broader lunar gravitational field. The moon's gravity is not uniform, with multiple small anomalies scattered across the surface. Each mascon contributes to this uneven field, combining with crustal variations, topography, and other density contrasts to produce a complex gravitational environment. Mapping these features is critical for precise lunar navigation and mission planning. The discovery of mascons has practical implications. For orbiting spacecraft, ignoring these anomalies can lead to unintended changes in altitude and velocity. Mission planners must account for the additional pull when designing stable orbits, particularly for low altitude reconnaissance or lander operations. Early lunar satellites demonstrated this need, and today, mascons are included in all precise lunar gravitational models. The study of mascons also helps scientists understand planetary impact processes. By comparing lunar basins with similar features on other planets or moons, researchers can determine how impact energy is distributed in planetary crusts. Mascons illustrate the combined effects of excavation, rebound, volcanic infill, and cooling, offering a detailed record of post-impact evolution. Observations from orbiters, such as the Lunar Prospector and GRAIL missions, have provided high-resolution maps of lunar gravity. GRAIL, in particular, allowed scientists to measure tiny variations in the Moon's gravitational field, revealing detailed structure of mascons and surrounding regions. These data have improved models of the Moon's interior density and crustal thickness. Mascons may also indicate deeper mantle processes. The uplift of mantle rock during basin formation brings denser material closer to the surface, contributing to the anomaly. Studying the magnitude and extent of these uplifts helps scientists infer the properties of the lunar mantle, including density gradients and elastic response to stress. The combination of seismic, gravity, and topographic data creates a comprehensive picture of mascon formation. Seismic studies help identify crustal thickness and subsurface structure. Gravity data reveal mass concentrations. Topography maps the shape of basins and surrounding terrain. Together, these measurements allow reconstruction of impact dynamics and volcanic history. Some mascons have associated magnetic anomalies, suggesting that impacts may also influence localized magnetism. The connection between mass, magnetism, and volcanic fill provides additional information about crustal composition and thermal history. Studying these relationships helps scientists understand the Moon's evolution on multiple levels. The uneven distribution of mass beneath the Moon's surface remains an area of active research. Scientists continue to investigate variations between basins, differences in lava thickness, and the role of mantle uplift. Each mascon provides a unique record of early lunar processes, including the timing of impacts, subsequent volcanic activity, and structural adjustments in the crust and mantle. Understanding mascons also informs future lunar exploration. Knowledge of gravitational anomalies is essential for stable satellite orbits, precise landing site selection, and surface operations. Accurate gravity maps reduce the risk of unintended trajectory shifts and help plan fuel-efficient maneuvers. Overall, mascons represent one of the Moon's most unusual and scientifically valuable features. They reveal the complexity of basin formation, the distribution of dense material, and the Moon's internal response to massive impacts. Continued study of mascons helps refine models of lunar evolution and supports a safe, precise navigation for future missions. The Moon's surface is covered with countless craters, ridges, and valleys that record a history of impacts spanning billions of years. Among these features, some remain puzzling because of their unusual formation patterns or persistent anomalies. One such category includes enigmatic surface deposits that do not match known volcanic or impact processes. These areas may involve unusual mineral distributions, layered regolith, or localized magnetic effects that alter surface characteristics in subtle ways. Remote sensing instruments have detected regions with unexpectedly high or low reflectivity. Variations in brightness, composition, or thermal behavior indicate differences in regolith properties. For example, certain patches may retain heat differently at night, suggesting variations in density, particle size, or mineral content. These subtle anomalies provide clues about processes that shaped the lunar surface beyond ordinary cratering or lava flows. Some anomalous regions are associated with localized magnetic fields. Measurements show that areas with unusual surface properties often correspond to small crustal magnetizations. These localized fields may interact with the solar wind, altering the rate of space weathering. This interaction can preserve brightness, change chemical composition, or modify the orientation of surface grains over long periods. In addition, the layering of regolith in these regions sometimes differs from surrounding terrain. Orbital radar and optical imaging reveal stratification that may result from repeated deposition events, such as micrometeorite impacts, ejecta from distant collisions, or ancient volcanic ash. Understanding these layers helps reconstruct the moon's environmental history, including periods of heavy bombardment and regolith development. Thermal anomalies are another feature of interest. Some areas retain more heat after lunar night, indicating differences in thermal conductivity. These variations suggest either differences in material composition or the presence of subsurface structures, such as buried lava tubes, denser rock deposits, or voids. Thermal mapping thus provides a window into both the composition and the structural integrity of the subsurface. Certain anomalies appear to evolve slowly over time. Long-term orbital observations show that changes in brightness, reflectivity, or local magnetic signatures occur gradually, implying ongoing interactions between surface material, micro impacts, and charged particle flux. Monitoring these changes allows scientists to study dynamic processes on a body that is otherwise considered largely inert. The origin of these unusual features may involve multiple mechanisms acting together. Large impacts can redistribute material and expose previously buried rock. Volcanic processes may deposit layers of differing composition. Localized magnetic fields can modify space weathering. Together, these processes create subtle, persistent patterns that challenge conventional models of lunar geology. Studying these anomalies enhances understanding of the moon's surface evolution. By analyzing how regolith properties, magnetic fields, and thermal behavior interact, scientists can refine models of crater degradation, surface renewal, and long-term modification processes. These insights are valuable for planning both robotic and human missions, as unusual areas may influence landing site safety and resource availability. Some regions also suggest the presence of previously unrecognized subsurface structures. Radar imaging indicates that buried lava channels, fractured bedrock, or compacted ejecta may contribute to unusual surface properties. Mapping these features aids in understanding the internal consistency and mechanical behavior of the lunar crust, providing context for seismic activity and surface stability. In addition, the study of surface anomalies informs broader planetary science. Comparing unusual lunar deposits with features on other airless bodies, such as Mercury or asteroids, reveals how impacts, thermal processes, and magnetic fields shape planetary surfaces under similar conditions. These comparisons help refine models of surface evolution in the absence of atmosphere and water. Overall, these anomalous areas demonstrate that the moon's surface is more complex than visible craters and Maria alone suggest. Variations in brightness, composition, magnetic influence, thermal properties, and subsurface structure all contribute to a subtle but scientifically significant mosaic. Continued observations, combined with sample analysis and orbital mapping, will improve understanding of these features and their role in the moon's geological history.